I went ahead and found those intersection points already. That part is algebra that hopefully you can figure out. So the particular question that I was asked about is revolving this around the line x equals -2 to set up the volume. And I'm happy to do any of the other parts of this problem, but I did want to start with that revolving around x equals -2. Well, -2 happens to be one of the intersection points between the two curves. So that's what I am revolving around. And when we're finding these volumes of revolution in the context of our 17B class, we're always going to be taking our arbitrary cross-section perpendicular to the axis of rotation. Since my axis of rotation is vertical, that means I need horizontal cross-sections. So my cross-sections are going to come in like this, and then when they revolve around that, they're going to revolve around in a circle. So there's my arbitrary cross-section. And in terms of the volume, I know that when I spin that around, I won't get something that's solid. I'll have something that's a little bit hollowed out in the middle, which means that I'm going to have a pi big R squared times a dy. And again, the dy, because my arbitrary cross-section here is horizontal, minus a pi times a little r squared dy. And both of those will be adding up calculus style. There are two complications in this particular question. One complication comes in the fact that because we're revolving around x equals -2, we're always going to find that radius, both the smaller radius and the larger radius, by starting at our axis of rotation and going until we hit an edge of our arbitrary cross-section. That means that our inner radius, oh, I used a big R, but I really meant to use a little r. Our inner radius there is the distance between x equals -2 and our parabola curve. So if this entire distance is 2, and if I choose a point here, that's the point x, then that radius we're looking for is really 2 minus x. So for now, I'm going to put that in as a placeholder over here, that our smaller radius is 2 minus x. And I said that's a placeholder because that x, I'm not going to integrate that x with respect to y. We're still going to have to come back and figure out what that equation looks like if we made it say x equals. For our larger radius, again, I'm going to start at the axis of rotation and come out until I hit the edge of my cross-section. So now I'm looking for that distance r. Similarly to our other piece here, if this entire width is 2, then the part we're looking for is 2 minus how far our x has come out from the line. Since this line is pretty easy to rearrange, I'm going to rearrange this line to say x equals 3 minus y. So for that larger radius r, I would be looking at 2 minus 3 minus y, that whole thing squared dy. Now we come to the part where we have to figure out what that x is for our inner radius. If I rearrange this equation to solve for x, so if I rearrange this equation to solve for x, then I'm going to subtract 1 and take the square root of both sides. So I'd have something that looked like y minus 1 is equal to x squared. Solving that for x, I actually get a positive and a negative square root, which leads me to the second complication of this problem, which is if I'm taking my arbitrary cross sections horizontally, then up here at the top, we can see that the inner radius is hitting the parabola and the outer radius is hitting a line. But we're going to get to a point where when we're doing those horizontal cross sections, my inner radius hits the parabola, but so does my outer radius. And that's where we need to take into account the positive and negative sides of this once we take the square root. This function right here actually turns into x equals the positive square root of y minus 1. And on this side, x equals the negative square root of y minus 1. It's this side that forms our inner radius when our cross section is up here. So coming over here, I'd want to replace this x with the negative square root of y minus 1. So I'd have 2 minus a negative, or 2 plus the square root of y minus 1. This would all be taking place for my slices in the y direction that come down as far as y equals 2 and up as far as 5. So this part would all have limits from 2 to 5. But we'd be adding in the part down here where when we look at that cross section, both the inner radius and outer radius are coming from that parabola curve. And those slices are occurring down here as low as y equals 1 and as high as y equals 2. So from 1 to 2, I'd have pi. We're going to have our outer radius times dy plus 1 to 2, that inner radius dy. I almost lost a pi in there. So for this outside radius, now I'm looking at this whole distance of 2 plus additional x distance. So this outer radius becomes 2 plus the square root of y minus 1. And for our inner radius, now I'm looking at 2 minus the x value, or 2 minus the negative square root of y minus 1. And in terms of the setup, we get to quit and walk away right there.